Welcome to this presentation on passive elements used in optical networks. My name is Pavel Schuster, and I have been working as a key account manager at Performed Line Products for 20 years. Our focus is on all types of housings used in optical networks, such as dome closures, distribution boxes, and cabinets. Today we will cover key terms and their meanings, essential knowledge for installation companies, network designers, and product distributors. We'll explore areas including network architecture, cables, housings, and other optical components and accessories. Let's get started. Time to begin with the different deployment models of optical networks. To start off, imagine fiber to the X as a magical internet ferry delivering blazing fast speeds directly to your device, wherever you are. FTTx plays a crucial role in next-generation access (NGA) networks, which aim to deliver higher speeds and improved quality of service. One of the early pioneers of fiber to the home was the Japanese company NTT, Nippon Telegraph and Telephone Corporation. Back in the 1990s, NTT worked with companies like AT&T, Fujitsu, and Hitachi to develop the essential systems for FTTH infrastructure. A major milestone came in 2004 when Verizon launched the first FTTH network in Keller, Texas. I like to describe FTTH with a simple motto. FTTx is like having a superhighway of internet speed right to your doorstep. Moving forward, fiber to the curb. Often used as a cost-effective alternative to FTTH, FTTC leverages existing copper lines for the last few meters to the customer's home. This makes it quicker and cheaper to deploy, while still offering improved speed and stability over traditional connections without the high investment required for full FTTH rollout. A small note for relief. Do you know why did the optical fiber go to the building instead of the home? Because it wanted to make a connection with everyone in the building. Finally, there's fiber to the room. This approach focuses on in-building installations, making use of existing conduits along floors, walls, or ceilings. Fiber is typically distributed from a central point, using waterproof tapes and micro-optical cables to ensure resistance to moisture and dust. FTTR brings fast, stable connectivity to every room, ideal for modern smart homes and high-performance commercial spaces. We have various optical network technologies categorized based on their design and application. Here are some key types. First, let's look at point-to-point network. A dedicated fiber connection between two endpoints, such as a user and a network provider, provides high bandwidth and a direct private communication channel, commonly used in enterprise environments for secure and fast data transmission. Next, we have gigabit passive optical network, a shared optical network where a single fiber line is split using passive optical splitters to serve multiple users, offers cost efficiency and scalability, typically used for residential and business broadband internet, supports high-speed internet, voice and video services. Another used option is Ethernet passive optical network, similar to GPON but uses Ethernet protocols for data transmission, designed for IP-based services and widely used in Asia for residential internet access. And as we continue, here are a few more types of optical and hybrid network architectures worth highlighting. Another type is active optical network. This is an active point-to-multipoint network where powered equipment, such as switches and routers, is used to distribute signals. It offers dedicated bandwidth to each user, but the need for active components makes it less energy efficient compared to passive systems. Next, let's mention radio frequency over glass. This architecture combines optical fibers with radio frequency signals to deliver cable television and internet services. It is typically used in hybrid cable fiber deployments, especially in regions transitioning from legacy coaxial infrastructure to fiber. Finally, there is hybrid fiber coaxial network. While not fully optical, this network integrates coaxial cables with optical fibers. It is commonly used by cable operators to provide broadband internet and television services, particularly in urban and suburban areas. Quickly, let's go through cable terminology. A loose tube cable is ideal for outdoor use, resistant to temperature changes, and often includes water-blocking compounds. A micro-loose tube cable offers key advantages such as higher fiber density, lower installation costs, and minimal disruption during deployment. There are several types of a ribbon cable, each suited for different needs. A flat ribbon cable has fibers in a straight line. great for mass fusion splicing. A spiderweb ribbon holds fibers together with a thin layer, but they can be easily separated. A rollable ribbon is more flexible and fits better in tight spaces. A mass fusion ribbon is made for high-capacity networks with many fibers in layers. When you combine this type of ribbon cable with the high-capacity Coyote Dome HD optical closure, the result is a truly high-capacity network capable of splicing nearly 7,000 fibers. These cables make installation and splicing faster and easier, which is why they're ideal for modern networks including high-density 5G. A central tube cable provides good protection for the fibers and is often used in indoor and outdoor applications. It's the most beautiful word in optical terminology. A pigtail is like the Swiss Army knife of the fiber optic world. It's got a connector on one end, ready to plug into your equipment, and bare fibers on the other end, ready to be spliced into your network. It's super versatile and handy, making it a go-to tool for quick and reliable connections. Think of it as the ultimate multitasker in your fiber optic toolkit. An armored cable offers enhanced protection against physical damage, suitable for harsh environments. An aerial cable is suitable for overhead installations, resistant to environmental factors. A distribution cable is easy to install and manage, suitable for indoor applications. A breakout cable provides strong protection for each fiber thanks to individual jacketing. It's durable, easy to handle and install, and flexible enough for tight or demanding environments. Thanks to its resistance to moisture, temperature changes, and wear, it's ideal for data centers, telecom networks, and industrial use. A patch cord is an optical cable used to connect devices. It comes in simplex, one fiber, or duplex, two fibers versions, and with different connectors such as LC, SC, or ST. Thanks to its reliability, it's widely used in telecom, data centers, and industrial networks. In optical cables, a buffer protects the fragile glass fibers from bending, crushing, and other damage. It also helps keep the signal clear by reducing reflections and shields the fibers from moisture, dust, and other environmental risks. The key features of a breakout or fan-out cable include, firstly, individual fiber protection. Each fiber is individually jacketed, providing enhanced mechanical protection and flexibility. Secondly, ease of termination. These cables can be easily terminated without the need for additional junctions or splicing. And thirdly, versatility, suitable for various applications, including direct connections to devices and use in rugged environments. So whether you call it a breakout cable or a fan-out cable, you're essentially referring to the same robust and versatile fiber optic solution. We're about halfway through the presentation. Thanks for sticking with me. Let's stay with the topic of cables a little longer. Now I'd like to walk you through some of the most common cable deployment methods. In other words, how fiber optic cables are physically installed in the field. Each method comes with its own pros and cons, and the choice depends on factors like environment, budget, and existing infrastructure. Let's begin with aerial deployment. In this approach, optical cables are suspended on poles or towers above ground. It's relatively low cost and makes maintenance or upgrades straightforward. The downside? Cables are more exposed to the elements, like wind, ice, or storms. That's why self-supporting ADSS cables are often used. These all-dielectric cables are made from non-metallic materials, offering excellent insulation, ideal for high-voltage areas or places with frequent lightning. Another cable deployment method is underground deployment, where cables are buried below the surface, either directly or inside protective conduits or ducts. This method offers strong protection against weather and accidental damage. However, it's more expensive due to the need for excavation and specialized equipment. And finally, there's facade deployment, a popular choice in dense urban areas where aerial or underground installation isn't practical. Here, fiber cables are mounted along building exteriors. It's a fast and efficient solution that still provides easy access when needed. It's quite popular in Spain or Belgium. Each method has its place. The best choice always depends on the specific goals and site conditions. Let's now take a closer look at some of the key techniques used during fiber installation and splicing. These methods play a crucial role in ensuring performance, reliability, and efficiency across different network environments. A fusion splice aligns the fiber ends precisely and fuses them together using an electric arc, offering the lowest optical loss and highest reliability with minimal reflection. However, it requires specialized equipment and skilled technicians. On the other hand, a mechanical splice uses a mechanical fixture to align and hold the fiber ends together, often with a gel or adhesive. This method is easier and quicker to perform without needing expensive equipment, but generally has higher optical loss and lower reliability compared to fusion splicing. A ribbon splice is a method used to join multiple optical fibers simultaneously, particularly useful for high fiber count cables. About the ribbon cables, we've already talked. This technique significantly reduces the time and effort required for splicing. Ribbon splicing involves splicing a group of fibers, typically 12, arranged in a flat ribbon configuration. The fibers in the ribbon are aligned and fused together in a single operation. There are two types of ribbon splicing: mass fusion splicing and mechanical ribbon splicing. Mass fusion splicing is the most common method, where all fibers in the ribbon are fused together using a fusion splicer, providing low loss and high reliability. Mechanical ribbon splicing is less common and uses a mechanical fixture to align and hold the fibers together, which is quicker but generally has higher loss compared to fusion splicing. Midspan is a technique where an optical cable is interrupted to add additional devices or cables. Basically, this technique is used for various purposes, such as dropping a small fiber count cable from a larger backbone cable, repairing fibers, or distributing signals to end users. The process involves removing the cable jacket, metallic or dielectric armor, and internal protective components to access the optical fibers without interrupting the flow of other fibers. Microtrenching is an innovative and efficient method for deploying fiber optic cables. It involves creating narrow, shallow trenches in existing roadways, sidewalks, or other surfaces using specialized machinery. These trenches, typically only a few centimeters wide and deep, are designed to house microducts or cables, which are then covered with durable materials to restore the surface. See photos from the field on this slide. Now let's move on to microduct systems, a key component in modern fiber network design. While naming conventions may differ from one manufacturer to another, the core idea remains consistent. A microduct system is a clever and compact way to organize and protect fiber optic cables using a network of narrow plastic tubes. These small conduits help maximize available space by allowing multiple fibers to be installed within a single larger duct. The system is highly adaptable, making future network expansions or upgrades much easier, especially as technology evolves and bandwidth demands increase. Plus, it's cost-effective because you can use existing infrastructure and avoid the hassle of installing new ducts. And don't forget, these microducts provide excellent protection for your fiber cables, keeping them safe from environmental factors and physical damage. So it's a win-win for efficient and scalable network installations. There are several types of microduct systems used for different applications. First, direct burial involves installing microducts that are specially designed to be buried directly in the ground. Connections and branching are achieved using durable connectors. Second, blowing into HDPE conduits is a technique where lighter profiles such as mini cables, micro cables, or bundles of optical fibers are inserted into high-density polyethylene conduits by blowing. Lastly, microduct systems can be utilized for indoor or aerial installations and are available in various configurations to suit different deployment needs. Let's now look at some of the key passive components used to organize, protect, and manage fiber optic connections across different parts of the network infrastructure. A multi-dwelling unit distribution box is a central point for connecting and organizing fiber optic cables in buildings with multiple separate housing units, such as apartment complexes. It simplifies network management by enabling structured fiber distribution to each individual unit, supporting easier installation, maintenance, and future upgrades. An optical distribution frame is used to terminate, splice, and manage optical fibers in one organized location. It comes in several versions tailored to different installation scenarios. A rack-mount ODF is designed for standard 19-tone equipment racks and is commonly used in data centers and telecommunications rooms where space is limited. A wall-mount ODF is installed on vertical surfaces and is ideal for building entry points or technical rooms. A floor-standing ODF is a larger freestanding unit that offers high fiber capacity and is typically deployed in central offices or large-scale telecom facilities. A fiber distribution hub provides a versatile solution for managing fiber connections in access networks. It supports both traditional splicing and plug-and-play pre-terminated systems. With its high capacity, an FDH is suitable for dense fiber deployments. It also offers easy front and rear access, which speeds up installation and maintenance. Built-in features for cable routing, such as hoops, clips, and tie-downs, help maintain clean and orderly organization inside the cabinet. A dome closure is a sealed enclosure used to protect fiber splices in both access and backbone networks. It's available in various sizes and configurations to accommodate different numbers of cables and splice trays, and it's especially well suited for outdoor or underground installations where durability and environmental protection are critical. Now let's focus on key passive components that enable the physical connectivity, splitting, and adaptation of fiber links in optical networks. An optical connector, sometimes referred to as a coupler, allows for quick and easy connection or disconnection of fiber optic cables, unlike splicing, which is permanent. Connectors come in various types such as SC, LC, ST, or E2000, each suited for different applications and environments. A MPO connector is primarily used in data centers, where it consolidates multiple fibers into a single compact interface. It supports parallel optics applications, which transmit and receive signals over multiple fibers simultaneously to achieve higher transmission speeds. A planar light wave circuit splitter, often called a PLC splitter, is used to split one optical signal into multiple outputs. There are several packaging types, each designed for specific installation scenarios. A bare fiber PLC splitter, exposed fibers at all ends, used in static environments like cable connector boxes or distribution panels. A blockless PLC splitter, compact and flexible, ideal for splice trays and tight enclosures. An ABS box PLC splitter, the most commonly used type, housed in a robust ABS plastic box for general indoor or outdoor use. A LGX PLC splitter, enclosed in a metal LGX cassette, designed for 19-inch rack or cabinet installations, offering plug-and-play convenience. A rack-mounted PLC splitter, built for high-density 19-inch cabinets in data centers and server rooms. An optical adapter is used to join two fiber optic connectors, often in situations requiring extension, testing, or repairs. It also plays a key role in network setups, connecting patch panels and enabling cross-connections between different connector types. Some adapters even convert between connector formats to ensure compatibility. There are different adapter formats based on capacity. A simplex adapter connects a single fiber, used in single-channel applications. A duplex adapter connects two fibers for bidirectional data flow. A quad adapter connects 4 fibers, ideal for higher density requirements. Adapters are also matched to connector types. SC adapters have a square profile and are commonly used in access networks. LC adapters are compact and ideal for high-density racks. ST adapters feature a round bayonet-style design, often used in field deployments. FC adapters use a threaded coupling for secure connections in demanding environments. Finally, an optical adapter can be designed for either single-mode or multi-mode fibers, depending on the performance needs of the network. I believe that each country has unique terminology, nicknames, and slang for various operations, materials, and moments encountered in the design and implementation of optical networks. This was just a sampling of those that are commonly used. If you have any questions, feel free to call me, send me an email, or connect with me on LinkedIn. My name is Pavel Schuster. Thank you for your attention, and I look forward to seeing you at the next webinar.